Hello, multivariable calculus students. This is Mr. Johnson, and this is the third and last video for section 11.2. And we're just going to end our study of limits in this section with continuity, which is a carryover from what we studied in the previous calculus classes we've had, where we have a three-part proof for continuity for any particular function. So the first part, as it's been in the past, is that f is defined at a given point that we're analyzing. The second part is that the limit exists at that point. And the third part is that not only does the limit exist, but the function exists, but they are the same. And that would be our definition or our proof of continuity. So in example 9, we're going to look at whether or not the function f of xy is continuous. And this is one that we had studied right at the beginning of the section. And we looked at the table and we said, yeah, this just doesn't seem like it's the case. And then we looked at different paths that we would take, and they did not agree. So we do know that this particular function is not continuous. We also know that the limit as y approaches 0, 0 does not exist. And so in this case, we know that this particular function, f of xy, is continuous for all xy in R2, such that xy does not equal 0, 0. And the reason for this is because f of 0, 0 does not exist. Okay, now again, we could have x equal to 0 or y equals to 0. We cannot have both equal to 0. Okay, let's take a look at number 10. So with number 10, we have a piecewise function. So if xy is not equal to 0, 0, then we have x squared y cubed divided by 2x squared plus y squared. And if xy is 0, 0, we have 1. So the question really is, what's happening at 0, 0? We know that as we analyze the function, x could be 0, y could be 0. They both can't be 0. And so therefore, it is not defined at 0, 0 with this piece of the function, but it is defined at 0, 0 at 1. So our real question here, or our determination of continuity, would specifically be the question, does the limit as x, y, when it goes to 0, 0 of x squared y cubed over 2x squared plus y cubed, does that in fact equal 1? Because if it does, then based on the definition or the proof of continuity, we know that the particular function is continuous. So what we're trying to show is that that is not the case, and therefore the function is not continuous there. So let's take an approach, and we could pick a variety of approaches. I'm just going to approach 0, 0 along the x-axis. Now, if that's the case, then y would be 0. So our function f of xy would be f of x0, which is 0 divided by 2x squared. And again, I'm using my definition. I am substituting y as 0, and I get 0 in the numerator over 2x squared, which of course goes to 0. So as xy approaches 0, 0, f of xy approaches 0 while we're traveling along the x-axis. All right, so what I'm going to do is I'm going to label this as L1, just to give it a name, okay? So what we've determined is that L1 is not equal to 1, which is what we were trying to shoot for here, and therefore the limit as xy goes to 0, 0 of x squared y cubed divided by 2x squared plus y cubed, y squared. No, you know what, I'm just going to go back here and fix this because I think I made a mistake at the very beginning. I just wrote a 3 there, so I apologize for that. You can change that to y squared. Does not equal the function value at 0, 0, which was 1, and that's what we were trying to prove. And so what we could say is that, and therefore f of xy is not continuous at 0, 0. Okay, let's move on to example 11. All right, example 11 is a little bit tricky, and there's the multiplication of xy here, which causes a slight change to some of the stuff that we had been studying up to this point with regard to limits. So I'm going to do this one a little bit differently. And again, we're analyzing continuity here. So the question, again, is we know that the first piece of this particular function is evaluated when x times y is not 0, and it is equal to 1 when x times y is 0. So the question really is, when we take the limit of this as xy goes to 0, then is it going to be equal to 1? Now the challenge here is that the point xy is not going to the point 0, 0. It's the product of xy that is going to 0. And so that's a difference that we really have not analyzed up to this point. So what we're going to do is we're going to define this a little differently. So first off, I'll just make the statement that sine of xy is a continuous function, right? There's no particular values of xy that would ever cause an issue with that particular function. Now, as we analyze the entire piece to this is going to be continuous for all xy in R squared, except when x times y is equal to 0, which again is our concern when it comes to continuity for this particular function. Okay, we're going to redefine a few things, and again, the reason for this is that as it stands, and I'm going to erase this, so hold on here. As it stands, this is not, even though this is what we've been often analyzing, this is not the type of a limit we are analyzing here, because we're looking at the multiplication of xy. So we don't care if the point goes to 0, 0. We care if the product goes to 0, 0, which is a difference. Okay, so we're going to redefine these values a little bit. What we're going to do is we're going to take and redefine a point. We're going to call it some arbitrary point. I'm going to use a and b. And we're going to let a and b be a point, just some random point in R squared, such that the condition here is that a times b is equal to 0. So we're setting a very specific point that causes a product of 0. Okay. I'm also going to let, I'm going to let t equal x times y, because I need to give xy a name, a product name, because I want to change my limit in terms of how it's set up. I want to reduce this down to one variable if I can manage that. Okay, as xy goes to AB, so as I map my xy point to my AB point, and again, my AB point is defined by, we've defined this as the product equal to 0. So as xy goes to AB, then t, which is the product of xy, would then go to 0. Because again, if the point AB is defined such that a times b is 0, well then if xy is mapped onto AB, then t, which is the product of xy, would go to then 0. Okay, so here's what we can do with our limit. So our limit, if we were to, for example, name it now as the point xy going to 0, 0 of sine of xy over xy, we can now change this limit into the limit as t goes to 0, our new definition of sine of t over t. Now this is one that, back a couple years ago you probably memorized. You could also use L'Hopital's rule to evaluate this now that it's down to one variable. But your limit is 1 for this particular function. So we have a situation where f of x, y is continuous because, based on our definition of continuity, the limit as xy goes to 0, 0 of sine of xy over xy is equal to the function at 0, 0. Now again, we've changed our definition here in terms of what points we're analyzing based on a and b, but we've proven that the issue we had with the original setup, when the product xy was equal to 0, we have a function value of 1, which is equal to that limit, and therefore this is a continuous function. All right, we're going to work on the last example, example 12. And we have a function arctangent of y over x, and we're asking the question, where is it continuous? So we're going to break this into two parts. Number one, if we look at just y divided by x, this is continuous for all points xy in R squared, except when x is equal to 0. If we look at the second part of the function, arctangent of, let's just say, a is continuous for all a in the real number system. So what we have for the question, where is the function h of xy continuous, we could say that h of xy is simply continuous. This is just a composite. Again, we're looking at y over x, the restrictions on that, arctangent, the possible restrictions on that. We're just going to be combining this composite function together. So h of xy is continuous for all xy in R2, and x cannot equal 0. All right, that does it for section 11.2. Thank you.